Hello, here we are continuing on with a 2012 PAT. These are the written answers in the physics section. So we've got a 12 volt battery, a voltmeter, an ammeter, a resistor, 2 kilo ohms, sketch below. Right, okay, I've just drawn these out down here. Sketch connections to create a circuit to measure a potential difference across the resistor and an electric current. How big is the current? Right, so we want the voltmeter in parallel and the ammeter in series. So let's connect the ammeter up, and then we can put this voltmeter needs to go around the resistor. So we connect it up to anywhere really, providing it's on that wire. You know, we could have drawn. Yeah, if you're connecting up wires, it doesn't matter whereabouts on the wire you join it. You know, that last line from here that I've drawn to there, I could have drawn it into here. I could have drawn it up to here. It doesn't matter anywhere along there. They're all at the same potential, so it makes no difference where we actually connect it. What else? Oh yeah, how big is the current? So we've got that the current is the voltage times divided by the resistance, which is, what was the voltage? 12, and the resistance was 2 times 10 to the 3. So we've got 6 times 10 to the minus 3, which is 6 milliamps. So that's done the first part. It's got a lot of work for 1 mark. Capacitor C of 4 microfarads. Switch S. But they've sketched out this. Okay, they've got a little sketch here where the switch is flicking backwards and forwards between the bringing on the, charging up the capacitor using the cell and then discharging it through the resistor. So sketch how the current depends on time from the moment TE when the switch is moved to E, closing the circuit. Estimate the time T after which the current is not changing significantly. After time TD. Right, well, let's start with the first thing. So how does the current depend on time? Right, so when you're charging a capacitor, the current's going to start off high and it's going to drop down in this fashion. So we're going to have that, it's starting at that 6 milliamps. So that's what it's starting at, 6 milliamps. And it will drop down to, well, it's going to be continually approaching 0. They've asked us to estimate the time T after which the current is not changing significantly. So should we say that it's not changing significantly when it's less than 1%? Should we go with that? I mean, this is open to interpretation what significant is. So we've got the time constant. So remember, the capacitance multiplied by the resistance, that is the time it takes to drop off by 1 over E, so down to around about 37%. So our time constant is 4 times 10 to the minus 6, that's our capacitance, multiplied by 2 times 10 to the 3. So we've got a time constant of 8 milliseconds. So if we want to get to less than 1%, then we're going down. So if we did another, we're more or less knocking 2/3 off each time, aren't we? So we'd have 2/3 down, then we'd go down 2/3 again, which would take us down to about 13% maybe. Then down to about, so that's with 2. Then if we did another one, we'd be down to 4 and a bit. So we're looking at, say, 5 time constants. So let's say around about 5 times CR. I mean, that's just, I mean, it says estimate and what significant is. At least we've given some idea of what we consider to be insignificant, less than 1%. So let's say that, so we'll say that T is equal to 40 milliseconds. But you could go for anything really by the look of it, as long as it's not huge. After or small, I mean, as long as it's got long enough to have reached down to not changing that much. So after time TD much longer than T, the switch is moved to D, right? So we've charged up the capacitor. Our current isn't flowing anymore. We flick the switch over to D. We discharge the capacitor through the resistor. So now our current, now we have to sketch the current again. So it's going to now be going that way. So it's going to be starting at -6 because we're going in the opposite direction. That's -6 milliamps. So yeah, the current has changed direction on this because now we're discharging it and indicating on your sketch the time interval T. So yeah, we'll have the same T on both of these. I'm not really too sure what that's trying to achieve, but I suppose they're trying to get you to show that T is on a relatively flat portion of the graph. So maybe make it flatter than I've drawn it on here, but it's the age-old problems of drawing on the screen. So yeah, it's a bit of a mixed bag. I mean, I know quite often people aren't that keen of having this level of uncertainty in a question when you're in an exam. It's nice to know that you're doing the right thing, and this has thrown in some uncertainty by having this interpretive bit about what is significant. But there you go. That's our question 18. Where we now question, oh, it looks like the standing waves one. So we've got question 19, loudspeaker L placed between a microphone and a screen. Okay, the loudspeaker emits sound of fixed wavelength lambda in all directions. When the screen is moving slowly to the right along the x direction, okay, so we move it over there, slowly in comparison with the speed of sound, the microphone records minima and maxima of the sound intensity. What is the distance between two screen positions giving successive maxima? Okay, right. So in this case, we're wanting to change the path length because we're going to get, we need the difference here. So we're doing that difference. You've got, if we're going directly from the loudspeaker to the microphone, we've got some distance x. And then here we're going there and back. So we call that D. So 2D has got to be equal to a wavelength. So we're going to, because that's why you're going to get constructive interference. So we're going to, what is it exactly asking? What is the distance between two screen positions? Right, so that distance is going to be a change. We need to get another lambda in there. So the change in position is going to be half a wavelength, because then you'll have half out and half back, which means we'll be back in phase again in order to have constructive interference. Right, would the microphone record minima and maxima if the loudspeaker or the microphone is moving along X instead of the screen? Right, so we need things that are changing D. That is the thing that really matters here, is changing that D. So because yeah, otherwise we're not getting things back into or out of phase. This is the only difference that we've got in path length. Whatever we change here, both routes are taking that part, so it just cancels out. It doesn't matter if we're going directly there or we're going there, back, and then to there. These bits are going to cancel out in terms of creating a phase difference. So the only thing that matters is the relative position of the loudspeaker and the screen. So moving the loudspeaker, then yes, but moving the microphone will be no. So that's what we've got for those, because yeah, moving the microphone isn't changing the bit that matters, isn't changing the D, it's not changing that delta path length. Yeah, nice question, that one. Thinking, didn't have to make any calculations, just talking through what it means to have standing waves and how they're created. All right, now we've got some radioactive decay. So they've given us these two isotopes here of uranium. So 238 with this half-life and 235 with that half-life. They've got the number of each of the nuclei. Yeah, fair enough. Relative abundance is defined as the ratio of 235 to 238. Okay, at present that is 0.0072. So we need to get the relative abundance 10 to the 9 years ago with lots of approximations that all make some interesting maths. So we're going to be using our n equals n0 e to the minus lambda t, which means we're going to need our lambdas, but they are log 2 over the half-life. So if we're going to get these things, let's write them out in a different way. So we've got n235 over n238. That's at present is 0.0072. So that will be equal, because let's write it out this way just so we can see more clearly what's happening. So we need to divide this for 235 by the one for 238. So we will have n0 for 235 divided by n0 for 238, that's the thing that we're trying to work out, will be e to the lambda t for 238 divided by e to the lambda t for 235. Right, okay, so what have we got? We got lambda t for 238 is going to be log 2, so that's 0.7, divided by the half-life, which is 4.5 times 10 to the 9, multiplied by t, which is 10 to the 9, just keeping everything in years. And then lambda t for 235 will be log 2, which is 0.7, I can write properly, divided by 7 times 10 to the 8 multiplied by 10 to the 9. So that is 1. Okay, and they're going to cancel. So that equals 7 over 45. So putting all of that into here, we've got then that the ratio that we're looking for, the n0 over n0, is 0.0072. I'm just rearranging it to make the ratio the subject, times e to the lambda t for 235, so multiplied by e to the 1, so 2.7, then divided by e to the, is that right? Yeah, divided by this thing, e to the lambda t for 238, which is, yeah, here we go. So it's divided by 7, oh yeah, 7 over 45. So e to the 7 over 45. Right, that's good. So that gives us e to, oh right, okay, that's going to be using this approximation. So that is 1 plus that. So we're going to be doing 0.0072 multiplied by 2.7 and then multiply by, what is this? So 7 over 45 plus 1 is 52 over 45. So multiply by 45 and then divide by 52. Okay, that's an interesting set of numbers. So 72 times 2.7, okay, let's make that 27, times 4.5, and we've borrowed 1, 2, 3, 4, 10 to the, that's not a point. Right, let's write this line out again. I'm getting this all in a mess. 72 times 27 times 45. That was what I was going for. I'll get rid of all the decimal places. Divided by 52 times 10 to the minus, how many did we have? So 1, 2, 3, 4, 5. Yes, 10 to the minus 5. Right, 72 and 52, 4s both go into those. So that's 18 over 13. 18 times 27 times 45 over 13. So that's sort of 2 there. 27 over 13. We don't have to get this too precise. So yeah, we're looking at about 2, so about 18 times 90. So 18 times 9 is 162. So what have I ended up then? I've taken away a 0, so by 10 to the minus 4. So that is, what's that, 0.12316. Let's count back. So 1, 2, 3, then we need a 0. So yeah, 0.016. Oh, I got there in the end. So yeah, the numbers were really quite fiddly. So I've just made that approximation there of making that a 2, saying that we got 18 times 2 times 45, so 90, and then the 13's gone. 9 18's 162, take the other 10 to raise that minus 5 to a minus 4. Go from there. So I don't see how this is helpful, having this as a paper where you can't use a calculator. I mean, I'm all for doing some decent maths on a pen and paper, but I really don't see the advantage of doing it with these sort of numbers. It just seems daft. Nobody would do this in real life. And for a start, you'd code this up as a computer program, or pull out something that you've already got in your library of computer programs you've already developed. I just don't see that simplifying that is in any way valuable. What is valuable is being able to understand what you're doing and rearrange these equations and get it into that form. It's just too much messing around. Anyway, that's the end of that question. I'm not a fan of it. Right, question 21. Meteoroid of mass m is on a circular Earth orbit of radius r, a few times larger than the radius of Earth. Okay, so it's not hitting anything weird. Derive an expression for the meteoroid's speed. State the meaning of all the symbols used. Right, well, we can do our F equals MA on this. Now, this is an approximation, but if we assume that the mass of the meteoroid is much less than the mass of the Earth, then you can do that GMM over R squared equals MV squared over R. Now, that is an approximation in the case where M is much bigger than M. Otherwise, you end up having an M plus M if you actually work through all of the mechanics of it, of having the two of them affecting each other significantly in the movement that they actually have. Okay, they exert the same force on each other due to Newton's third law, but it has less of an effect on the motion of Earth. So, but inside that approximation, this is fine. We can cancel those, that and that. What we're trying to get the speed. So V is going to be the square root of GM over R. I think they've already, did they use R? Yeah, so they've already given us R, but they want us to state the meanings. So we have to say that M is capital M is the mass of the Earth, and that G is the gravitational constant. So that's so far so good. Another meteoroid of the same mass is on the same orbit in the same plane, rotating in the opposite direction. Okay. At an azimuthal angle phi 0, see below, right? All right, they hit each other. Coalesce. Sketch the complete trajectory of the newly formed double mass meteoroid, showing how the azimuthal angle depends on distance r. Sketch also its kinetic and well, I'll worry about that next bit afterwards. So we're going to have, well, from conservation of momentum, it's going to be that the V combined is going to be equal to 0. So the angle isn't going to change. They're just going to hit each other, coalesce, and then they're just going to drop straight down. Kind of a weird situation, but you would never actually get this to happen in reality. But at least in the theoretical scenario they've given us, that is what is going to be going on. So the angle is going to remain unchanged. So that's our phi with what we're doing. We're doing, yes, how it depends on r. So we're going to have our phi 0, and the radius will go from R, is capital R, is going to be our maximum, and it will drop down to, yeah, I called it RE. Yeah, I can see it here. It can't go any lower than RE, and it's just going to stay constant. Okay. Sketch also its kinetic energy and expected meteoroid surface temperature as a function of R. Give a very brief explanation of why you expect the temperature to depend on R that way. And for R is less than twice the radius of the Earth, the effects due to the Earth's atmosphere cannot be neglected. Right, so we've got to do kinetic energy and temperature as a function of R. Right, at least both of them are going to be positive. So we can draw this out with some wonky axes. So that's R, that's R, that's our temperature, and that is our kinetic energy. So when they hit each other at R, so that's where they hit there, they've got no kinetic energy at all, because we just said that from conservation momentum. When they crash at RE, they're going to suddenly drop down to zero, but they would have some kinetic energy when they hit the ground. So we're going to need a vertical line there. So the kinetic energy is going to increase. It's going to have a maximum. The atmosphere kicks in at 2RE. So that's going to be where we get a peak. So we need to, well, how are we going to get these things to join up? Right, so kinetic energy, the energy transferred, the kinetic energy is going to be our integral of force over distance. So that is the integral of gmm over r squared with respect to r. So our kinetic energy is going to be proportional to 1 over r when we integrate that, because that's r to the minus 2, it will go r minus 1. So this is going to be like 1 over r. It's going to go like that, which makes sense. You know, there's more potential energy. The closer we get to the Earth, the energy goes up, so the kinetic energy is going to increase. What are we going to get on the other side then? When we then get to the other side, the kinetic energy, well, it's going to start, yeah, it's going to start, we're going to be losing kinetic energy because we're now, I suppose we don't know, it might go up a little bit more, but it's going to, so the peak is actually going to be slightly to the left of the 2RE, because we're still going to be gaining kinetic energy, but just at a slower rate. And then eventually it's going to drop off and it's going to go for head towards a terminal velocity. Right, so that's become a bit, is this the one they've asked us to explain as well? No, it's only the temperature one. Right, okay, but once we got into the atmosphere and we just got free fall, we know it's going to head towards terminal velocity. So we're going to have it going that way in the atmosphere and then transition into this 1 over r thing. So that's the shape that we've got, with a peak probably just to the left of 2RE. That's what I would draw if I had more space on the screen. So what's happening then with the temperature? So we start at some temperature at R where it collides. Then it's going to be, so when it's out in space, it's going to be cooling until it hits the atmosphere. Not a lot, but it's going to cool slowly until we get down to the Earth's atmosphere at 2RE. We know when it hits the ground, we're going to get a big spike in temperature because the thing's going to vaporize. So we're going to end up going super hot over here. Now we're going to have air resistance, which is going to increase the temperature. So how is that going to work? It's going to go up in some way, but it's going to be cooling more. It's not obvious exactly how that's going to transition on all of this. So, but we need to explain things. So we can say this is cooling due to radiation in space, due to radiating in space. Then we're going to have heating due to air resistance, from air resistance. And then we're going to have, well, very sudden heating due to impact. Sudden heating on impact. So I suppose the question really is, what shape of line have we got due to the air resistance? And how much is that going to be heating? It's going to start dropping off, isn't it? Because we're going to be approaching a terminal velocity. So you're going to get an increase and then a decrease. So we're probably going to get something that's going to start going up, get steeper, and then you're going to inflect down, and then we're going to go up. I would expect you get something like that that's going on, but who knows exactly. Yeah, that's quite an involved question, that one. That is difficult. Again, it leaves a lot of uncertainty in the mind. There's no calculations here. Okay, there was calculations on that one. There's no calculations there, and they had uncertainty on that one. So they've left a lot of uncertainty in the mind of the student. I think that's the last question in this particular block. But yeah, without having definite calculations, it worries people. And I mean, I'm not it's a interesting sort of question, but it seems to be very much detached from reality. As soon as we see this two meteoroids in exactly the same but opposite orbits, then you're trying to describe things which are not entirely intuitive. So I would say they're very difficult questions, and this has been a difficult paper all round. And I know, although I haven't got onto it yet, but I have seen it in the past, the question that this paper winds up on is just different planet. So yeah, this is a really tough paper. Don't take it as a measure of, oh, I need to be getting all of this right if I'm going to get through a PAT test. This is overkill in my view.